LiDAR is an acronym derived from the phrase light detection and ranging. It is an active remote sensing technique that uses laser scanning to directly collect three-dimensional data for mapping purposes. The presentation explains the fundamentals of lasers used in remote sensing and the physical principles affecting the use of lasers in ranging, profiling, and scanning applications. This is the first of 4 RLOs developed on LiDAR remote sensing. 3 related RLOs that cover systems, data collection, data analysis, and applications are also available. The term remote sensing is used to describe the measurement of object properties by acquiring data from a sensor at a distance from the given object. By using spectral and radiometric data captured by a sensor, information about an object's properties can be determined more efficiently across greater spatial areas than in situ measurements alone. An in situ measurement is a physical measurement of an object. For example, to create a map of impervious surfaces with a large spatial extent such as the Broward County Land Use Land Cover map in the left figure, it would be impractical to measure every concrete and asphalt structure in Broward County with GPS measurements. A remote sensing scientist can use a sample of in situ concrete and asphalt points as training data for the creation of a supervised classification map of impervious surfaces. Remote sensing techniques are either passive or active. Passive remote sensing measures radiation naturally reflected or emitted from the ground, the atmosphere, or the clouds. The primary radiation source for passive remote sensing is the sun. Thus, passive remote sensing satellites such as Landsat and MODIS constellations operate only in daylight conditions. Active remote sensing systems make measurements using an artificial radiation source. By using a non-solar radiation source, active remote sensing instruments are not restricted to daylight operation. Earth-orbiting synthetic aperture radar satellites such as TerraSAR use radio waves to measure the digital elevation of surfaces. LiDAR and sonar use light and sound waves respectively for three-dimensional measurement of surface features. Technological advances in laser and inertial measurement technology have made LiDAR remote sensing one of the most significant contributions to topographic mapping over the past 2 decades. Airborne topographic mapping was primarily completed with photogrammetry in the latter part of the 20th century. The primary advantage of using LiDAR is the ability to directly collect three-dimensional data. To derive the same 3D data, traditional photogrammetric methods require additional intermediate steps, including the construction of stereo models from aerial imagery. As a mainstream mapping technology, LiDAR data is collected routinely from both terrestrial and airborne platforms. This image depicts LiDAR data of a condominium building on the Intercoastal Waterway in Miami, Florida, from a terrestrial LiDAR scanner. The terms LiDAR and laser scanning are used interchangeably. Before discussing how laser scanning works, the properties of the laser beam need to be understood. Laser is an acronym for light amplification of stimulated emission of radiation. Each LiDAR system uses collimated light from the electromagnetic spectrum ranging from ultraviolet through infrared. Collimated light is light whose rays are parallel. Without diffraction, these rays would spread without divergence over an infinite distance. The choice of wavelength for a particular system is dependent upon range performance, atmospheric and water absorption, eye safety requirements, and the reflectivity of the materials being measured. Most LiDAR systems use wavelengths in the near-infrared region of the electromagnetic spectrum as shown in the graphic by the red arrow. Bathymetric systems are an example of a LiDAR system that require the laser beam to penetrate the water for mapping of the bottom of the water body. Since infrared light is absorbed by water, an additional laser beam in the visible green spectrum is used to penetrate the water column and reflect back to the laser scanner. There are 2 primary methods of laser ranging described by the type of laser pulse emitted. The first one is the time of flight method. For the time of flight method, the laser ranging instrument emits a very short and intense pulse of laser radiation. The pulse travels from the instrument to the object being measured and then returns back to the laser ranging device. Since the speed of light is known to be approximately 300,000 kilometers per second, the precise laser pulse travel time interval is used to determine the total distance the laser pulse traveled. The distance between the object and the ranging instrument is half of the total time interval multiplied by the speed of light. The timing must be very precise because 1 nanosecond corresponds to a 30 centimeter travel distance. The alternative method for laser ranging is the continuous beam or continuous wave method. The range value is determined by comparing the emitted signal with the received signal. A phase shift in the sinusoidal wave between these two signals exists. This phase shift is added to the total distance of the complete wavelengths and divided by 2, which gives the slant distance. Laser beam divergence, surface reflectivity, and target interaction are three important properties that affect laser ranging quality, precision, accuracy, and intensity. These properties will be discussed in greater detail on subsequent slides. Laser beam divergence is a property that affects all laser ranging devices. The beam spot size on an object increases relative to the increased distance the object is away from the light source. An increased spot size makes detection of individual objects and object details more difficult. In the figure, there are 3 objects for each type of laser beam. The low divergence laser beam can detect these multiple objects with multiple small spot sizes. The wide divergence beam cannot distinguish the multiple objects with the larger spot size. Target interaction, specifically the angle of incidence or AOI, is another property that affects laser beam intensity. As shown in the figure, the AOI at which the laser beam hits the ground surface is constantly changing during a scan due to the sensor scan angle and local terrain slope variations. The sloped terrain causes elongation of the laser footprint. With an understanding of properties affecting laser ranging, we can now discuss one of the simplest LiDAR instruments, the laser profiler. This ranging device determines terrain profiles along a given line by providing a vertical cross-section of the topography. For stationary devices, the ranging device changes the scan angle along the line being measured. The figure shows a terrain profile where the vertical angles between successive points and slant ranges are used to determine the difference in height between 2 points on a given vertical terrain profile. The 2 images show a civil infrastructure application of laser range profilers. The rotating laser range profiler is mapping cross-sections of underground pipe debris and deformation information at regular intervals. The remote-controlled truck stops at each interval and the rotating head of the profiler incrementally changes the scan angle to provide the 360-degree cross-sections. When using an airborne platform, the laser ranging device is pointed vertically toward the ground. In this configuration, the profiling device is called a laser altimeter. Successive points are collected as the platform moves along the flight path. The forward movement of the aircraft provides the third dimension necessary to create the terrain profile. The figure shows a satellite laser altimeter swath from the NASA satellite ICESat, which stands for Ice, Cloud, and Land Elevation Satellite. ICESat measures terrain profiles in polar regions. This RLO presentation introduced the topic of LiDAR remote sensing as an active remote sensing technique. The properties and characteristics of lasers were discussed. Further, the use of lasers for ranging and profiling in remote sensing applications were explained. We conclude this presentation with a list of further reading on LiDAR principles.